righty then. Well, I guess the name of this session is Torque and Rotational Statics, but I was going to mostly talk about rotational inertia today because I feel like that's a bit of a tricky topic for most folks, and it's kind of the underpinning of all of rotation. So pretty much today and the 5 days next week are going to all be on rotation. So I'm going to go with rotational inertia. I think it's a foundational concept to start rotational dynamics with, and then the week after that we're going to have our live practice AP exams. Ooh, I know, right? Isn't that exciting? All right, so my name is John Frensley. I teach at Prosper High School in Prosper, Texas, about 30 miles north of Dallas, Texas area. And we're going to talk about rotational inertia. And there's not a lot to say on it. So I kind of struggle with like, how am I going to fill 45 minutes of time? So, and watch me, I'll go over time again. I always do it. This is going to be a really long warm up because this one I'm going to want you to really think and write and maybe even draw. And I know on the real exam, you're not going to be able to draw anything, but I think drawing is important here. And this might be something that interests the teachers who are watching. So I'm way big into performance-based assessments. I think it's a lot more fun than pencil and paper testing. I still do pencil and paper testing because the AP exams would have been a pencil and paper test. Let's just put it that way. But I like these because they're more fun for the students. They're more fun for me. So one of my performance-based assessments in Physics C is that they are going to make something called a slow-yo. And if you know who Stephen Yale is, he gave me this idea. He's with National Math and Science Initiative now, but I always want to give a shout out to people who give me good ideas. So the idea is, excuse me, I'm allergic to all this physics. So what I'm thinking is you're going to build, it's like a yo-yo that unrolls, but your goal is that it unrolls, but it takes the longest possible time to unroll. So I assign this to my students. I say, build it, bring it, and you're going to not only, the competition is it has to unroll, it can't stop on the way down, and it has to take the longest possible time to unroll. And so I say, and one of the things I learned from the first year that I did this is that the students have to have a round central axis, obviously, but unlike a yo-yo, which has one string coming out of it, there has to be two strings coming out of this, one on each end of the axis. If not, it becomes unbalanced and it flops over, it doesn't work. So for those teachers who want to assign this next year as a performance-based assessment for rotation, that's the first thing you need to know. So I have my own pieces of nylon that I give the students on the day of. We're on the second floor, so we do over the balcony onto the first floor, we time it. So here's what you're gonna do, students. I want you to brainstorm what kind of common household items there might be. You're not actually going to build it, but you're going to design it. And I want you to design from common household items. What would your slow yo look like? Be specific about what materials you would use and how you would put them together. And maybe on your piece of paper that's with you, you're going to make a little sketch. All right. So you're going to start with what's the central axis going to be made out of. We're going to pretend that strings are on both ends. And then you're not only going to design it, but I want you to tell me, why did you make the design choice you made? I did this because I think this is going to make it take longer to reach the ground, and talk about why. Talk about physics quantities, right? So I'm going to give you 5 minutes to, on your paper, design your slow yo. On your mark, get set, go. Okay, well, that was a lot of fun. So let's see. So what did I do? So my central axis was a chopstick. Okay, so I had a chopstick, and that's what the little threads went around and then up to where we hung it from. So I have this chopstick as my central axis, and I took some wire hangers. And Mommy didn't care for this, but I took these wire hangers, I straightened them out, and I straightened them into two wire hangers that made a cross. And I put one of those crosses on each end. So you imagine a cross. I put one on each end of the chopstick, right? And I glued it with hot glue. And then I stuck these clay balls, and I was very careful to make sure they were all the same mass as best as I could. So you have a chopstick, and on each end it was like a cross of wire hangers and then clay balls. And then I would just let that go, and it took a very long time to unroll. So how do you know if you made good design choices? So here's a little 7-point rubric for your design. First of all, you chose a central axis that's very, very thin, small radius. Now remember, it wasn't enough to make a good design choice. I asked you to explain why you made that choice. So if you chose a thin central axis, like I chose my chopstick, the reason for that is that the ropes produce torque. Those tensions from the two ropes produce a torque about the central axis. More torque comes from more radius. So I'm thinking more torque means a faster rotation. So I don't want that. I want the opposite. So I'm going to have a thin central axis to reduce the torque. So I say you chose a thin axis. You said that the thin axis makes less torque because less radius of action for your tensions. Less torque is less angular acceleration. Less angular acceleration is a longer time to fall because you don't get as much rotational speeding up motion. And then I chose to attach items to the central axis that were distributed far away. That was the point of the two cross pieces at the end with the clay balls at the end, was to get lots of mass far from the center. So the rope is close to the center, but the rest of the mass is far from the center. Why did I do that? Because that increases rotational inertia, which decreases angular acceleration. So I go for the least torque from the strings, small radius, and the most rotational inertia. The mass is far away. You'll see a sketch of my design a little bit later on. Okay, so what are we going to do? We're going to talk about what rotational inertia is, and define what it's what it depends on. We're going to talk about how rotational motion is affected by your rotational inertia, right? And we're going to formulate some experimental procedures to calculate the rotational inertia of an object. For those of you who are watching from P1, I'm just going to tell you right now that the first third of our discussion is going to be meaningful to you. The middle third is definitely not for you because it's going to involve some calculus for physics C. Then the last third is going to be about experiments to find rotational inertia, which I don't think an experiment-based question is going to be on the P1 or P2 exams this year, so it might not interest you. But in general, it would interest a P1 student if we were taking a regular exam this year, okay? So I want you to think to yourself, what is mass, right? Like, well, it's the amount of matter in something. That's true. But I say that mass could also mean how difficult it is to change the motion of an object. So for example, you think about a baseball, right? Okay, throw the baseball. Well, that's not that difficult to do because it has not very much mass. Easy to make it to go from stop to go. And if a baseball's coming at me, I catch the baseball, it's easy to make it go from going to stopping. It's easy to change its motion. It doesn't have a lot of mass. Now, if you like throw a school bus at me or something like that, and I hold up my little baseball glove with the school bus coming at me at 90 miles per hour, probably not going to be able to change its motion very much because it has a lot of mass. And then if you say, hey, Friendly, here's a school bus and it's in neutral, so there's no friction, please get it up to 90 miles an hour. Probably not going to be able to do that like I could a baseball. If you think I'm throwing a baseball at 90 miles an hour, you are crazy, right? So we give another name to mass. We call it inertia. We might need to give it its full name, translational inertia, how difficult it is to speed up or slow down left, right, up, down motions, right? So in rotation, there's an analogous quantity called rotational inertia, and it's a number. And it's a number that tells us how difficult it is to speed up a rotation or slow down a rotation, right? So if you have a wheel that has low rotational inertia, it's easy to get it to go and easy to get it to stop. But if a wheel has a lot of rotational inertia, it's difficult to get it to go, difficult to get it to stop, right? Okay, so rotational inertia symbol's capital I. The units are called kilograms square meters, right? It depends. Look at the units. It depends on two things: how much mass there is and how far the mass is spread from the central axis of rotation, right? So more mass, harder to rotate. Farther the mass is from the center, harder to rotate, right? Okay, so if you want to try a little experiment with rotational inertia, just get some kind of cylinder, for example, a pencil, what might work, or a roll of paper towels. Right now, I have my 20-pound barbell right here, right? And so if I take the 20-pound barbell and do this, this is not difficult. This is not that difficult to speed up and slow down its rotation. Why? Because all the mass is close to the central axis. But if I do this instead, this is more difficult to get it to speed up and slow down in its rotation because the mass is farther from the central axis. So in the case on the left here that I'm pointing out with my mouse, that would be easier to spin, get it going and get it stopping, twist it, because the mass is close to the center. Whereas on the right-hand side, that's going to be more rotational inertia because it's even, the mass is far away from the center. And then if I do this, and then I grab it by the end, which is really difficult to do because it's 20 pounds, and I do this, well, now there's even more mass away from the center. So if I choose the center of mass, the mass is close to the axis and I get the least rotational inertia I can. So if I choose any other point, then this mass is now farther from the center and it's going to contribute more to the rotational inertia. So rotational inertia depends not only on the object and its shape, but which axis you choose. Okay, so here's a more complicated experiment. Hopefully you can see this little animation on the side. You see a green wheel and a red wheel, and they both have 4 masses attached to them. So we see 2 pulley wheels. The wheels are identical. The wheels themselves are identical, but each one has 4 gray masses attached. So let's say the green and the red wheel are identical, and all 8 masses that are gray are identical to each other, right? But the green wheel has the masses close to the center. The red wheel has the masses farther away from the center, right? So it turns out that if you hang identical masses from these pulley wheels, the one with the masses closer to the center is going to have an easier time getting to rotate. It's going to have an easier time getting it up to speed. So with masses near the center, that's less rotational inertia. It's easier to get the green wheel to go. The red wheel has the masses farther from the center. It's harder to get it to go. But inertia goes 2 ways. Not only is it more difficult to get the green wheel to, more difficult to get the red wheel to go, it's going to be more difficult to get the red wheel to stop as well. So here's another experiment you could do. And hopefully you've seen this experiment maybe in your classroom where your teacher takes 2 objects that are the same mass, but they're not the same rotational inertia. For me, it's a puck. It's a black giant wooden puck, and it's the same size, same mass, but it's a metal ring, like totally hollow, right? So I call it the ring and disc or something like that. Hopefully you've seen something like that from your teacher. So the disc has atoms at the middle, atoms in between, atoms on the outside, but the ring has all the atoms on the outside and nothing in the middle. So the ring has more rotational inertia because its atoms are farther from the center. So the ring would be like the red wheel and the disc would be like the green wheel. And so the more atoms you have toward the center, that's less rotational inertia, easier to rotate, right? So now, now the 2 wheels are set on the same incline. The red wheel has more rotational inertia, harder to get it to go. The green wheel has less rotational inertia, easier to get it to go. But if you're harder to get you to go, it's harder to get you to stop. If you're easier to get you to go, it's easier to get you to stop. And that's what's happening here. So what's happening here is we now have the red and green wheels are both approaching an incline. The red wheel is harder to get it to stop rotating. So since it's harder to get it to stop rotating, it climbs up the hill farther. Whereas the green wheel is easier to get it to rotate because it has less rotational inertia. It doesn't climb as far up the incline, right? So that's the idea of this rotational inertia thing. More rotational inertia, harder to get you to start rotating, harder to get you to stop rotating. All right, so that's the basics of rotational inertia right there. All rotational inertias have the same form of an equation, right? So if you're like, hey, what's the rotational inertia of a ring? And I would say mass times radius squared. Well, what's the rotational inertia of a disk? Well, that's 1/2 mass times radius squared. What about a sphere? That's 2/5 times mass radius squared if it's a solid sphere. If it's a hollow sphere like a basketball, it'd be 2/3 mass radius squared. So here, it's always mass radius squared, and there might be a fraction out in front, right? So I is the rotational inertia, m's the mass, r is the radius. A little bit later on, we're going to talk about the rotational inertia of rod-shaped things rather than circle-shaped things. So what's a circle-shaped thing? Cylinder, ring, sphere. A rod-shaped thing like a baseball bat, we're going to use L instead of R, right? But it's still ML squared rather than MR squared. It's mass times the length squared. There's still going to be a fraction out in front. Oops. And I have a name for it. I call the fraction, that K, I call it the shape constant. And I call it the shape constant because literally it just depends on the shape. So all spheres are 2/5 mr squared if the sphere is completely solid, 2/3 mr squared if the sphere is hollow except for the very outside, right? So that shape constant depends on the shape. It's a number that's 1 if all the atoms are on the outside, less than 1 if some of the atoms are distributed closer to the axis, right? And it has no units, all right? So here's an example, right? So so the shape determines the shape constant. So this is my ring right here, and that's on the left, and that has a shape constant of 1 because all the atoms are the same distance from the axis. So all the atoms are 1 full R from the axis. So if I average every atom's difference, I'm going to do like an average, like R, 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 going around. I'm going to turn into a pirate here if I'm not careful. Then the average of all the R's is 1R, so then the rotational inertia is mr squared. But for a disk, the rotational inertia for a disk is 1/2 mr squared because some of the atoms are near the middle, some are in the in-between, some are on the outside, and there's an integral for those of you who are calculus enabled that's going to kind of average all that out for us, and it's going to spit out from a power rule the shape constant of 1/2. So the disk shape constant is 1/2. It's averaging the atoms in the middle that don't contribute a lot to the rotational inertia, the atoms in between that contribute some, and the atoms on the outside that contribute a lot to the rotational inertia, and the calculus just spits out 0.5. Now, a sphere shape constant is less than a disk. It's actually 2/5 or 0.4. So I want to talk about why it is a solid sphere has a little bit less shape constant than a disk. So here's a side view of a sphere. So I want you to imagine a cylinder, and you can see the cross section of the cylinder here in red. So you can't see the top of the cylinder. I'm kind of trying to signal it with my little mouse here, and the bottom of the cylinder, right? But that red cylinder made of atoms are all atoms that are close to the axis. They don't contribute a lot to the rotational inertia. So think about all the cylinder. If you're in calculus, you'd know about the shell method, right? So go ahead and cringe now because I just said it. So I want you to imagine doing a shell method on this sphere where you have a cylindrical shell that's like right on the axis, and those atoms contribute nothing. And then this red cylinder contributes just a little bit. And then this green cylinder out here, look at that green cylinder out here. They contribute a lot to the rotational inertia. But here's the problem. Because the sphere shape tapers off as it gets to the end, right? That's a sphere. Your atoms that are close to the equator that contribute a lot to the rotational inertia, there ain't as many of them as there are for a disk. So a disk has a lot of atoms around that outside. A sphere has a little tiny belt of them that's the equator. So less atoms close to the or far from the axis, less atoms far from the axis, that's a lower shape constant. Okay, so there's more red atoms contributing very little, less green atoms that are contributing a lot compared to a disk where there'd be a lot of green atoms on the outside and few red atoms near the middle, right? Okay, you are not expected to memorize the shape constants on the AP physics exams. The only shape constant you absolutely have to know is that if all the atoms are the same distance from the center, like a ring, then the shape constant is 1. That's the only shape constant you have to memorize. Other shape constants like 1/2 for a disk and 1/4 for a sphere, you would be given them if you needed them. And if you didn't need them, you wouldn't be given them, right? Okay, it's pretty simple like that, right? So just don't memorize any of the shape constants. If you've been in the business as long as I have, you've memorized a bunch of shape constants just because you've been around, right? Okay, just like you memorize the streets near your house if you've lived there for a long time, right? But we don't expect that out of students, right? Okay, so this is the part where we're gonna do a little calculus. I know that everybody loves that, but you may be asked to I don't think you're going to be asked to actually take an integral, but you might be asked to talk about one where you have to calculate the rotational inertia of an object. So do you remember 2 lessons ago with me when we had, it was called center mass, and I said, in order to find the mass of an object that has differing density at different points, you had to first of all have a function. So this function is called lambda, and it's a function of x. X is where you are on the rod. Lambda is called the linear density. So I know that density, like in chemistry, is mass per volume, but linear density is a mass per length, right? Because we're talking about a rod, so volume really doesn't matter for that, right? Okay, so lambda is linear density. So X might be the left-hand side. And then let's pretend that black is low density and white is high density. So then lambda would be a function that's returning a bigger and bigger density value as X gets bigger in this little picture right here, right? So how do you take lambda and you get the total mass? Well, you just integrate lambda dx and make sure you use limits. So anytime you talk about an integral or do one, there better be limits. That's an important rule in AP exam. Don't say integral without talking about limits, okay? So we're going to integrate, and we're going to integrate from the left side to the right side. So if the left side is x equals 0 meters and the right side is x equals 2 meters, we're going to integrate from 0 to 2, the lambda dx. And then remember, when you integrate a function from 0 to 2, you should get a number out for that, right? You're going to use one of the fundamental theorems of calculus. Here's the rotational inertia. Do you remember how I said it was mass radius squared? Well, mass is the lambda dx, and the radius squared is the x squared. So I is the integral of mass, lambda dx, times x squared. But here's the kicker. X equals 0 has to be the location of the axis. That is not required for the total mass integral. For the total mass integral, you can put x equals 0 wherever you want on that bar and you'll get the same number. But for the rotational inertia, x equals 0 has to be the location of your axis. If you move x equals 0 to a different place, you'll get a different rotational inertia because rotational inertia depends on your axis. Okay, here's a little guided practice. So I want you to pretend like you're given a rod and it has uniform density. So the density is just C. That's the easiest function in the world to integrate, right? Just integrate C in order to get the total mass, okay? Now, x equals 0 is the center and the length of the bar is L. So watch my mouse. This point right here is x equals 0, x equals negative half L, x equals positive half L. I want you to determine the mass of the bar in terms of C and L. If you have to take an integral, take an integral, but because of the uniform density, it's actually much simpler than that. And then I want you to derive, this is going to require an integral, the rotational inertia in terms of M and L and not in terms of C. So if you take an integral on the second part, you're going to get a C and an L in the answer, but you're going to use your answer to the first part to make it M and L. All right, I'm going to give you 3 minutes. On your mark, get set, think. That's not the song I wanted. Let me try. That's the song I wanted. Oops. ran out just a little bit before the time did. So you got 7 more seconds. My producer's going to laugh at me because I'm like, I have a new way of arranging my music on my little screen so it doesn't screw up, and it's screwed up twice already. All right, so there you go. Obviously, I don't know what I'm talking about. All right, the total mass is just the constant times L. It turns out if the density is uniform, you don't really actually have to take an integral. You just have to take the constant density and multiply by the length in this case, because C is mass per length, right? So no integral is really needed for that, but this we need an integral for. Now I can't typeset the limits here in PowerPoint. I haven't figured out how to make the limits there. So I put the limits out here to the right. So I'm going to integrate lambda x squared dx. And because this white dot is x equals 0, the axis, then I'm going to go from negative half L to positive half L as my limits. So I plug in my function. Okay, and the density is just C. Okay, the density is just C, so that's easy. Cx squared dx. So then I'm going to integrate that. So the integral of cx squared is 1/3 cx cubed. And I have not applied the limits yet, so I'm still indicating my limits here. So now I'm going to plug in 1/2 L into x cubed minus what I get when I plug in negative 1/2 L. So I plug in 1/2 L minus what I get when I plug in negative 1/2 L. So it turns out this winds up being 1/24 L cubed. This winds up being negative 1/24. So when you subtract a negative, you actually add. So 1/24 plus another 1/24 is 1/2. And you actually get, wait a minute, 1/12, I meant to say. 1/12 sounds familiar for a bar. Sure does. But if M is C times L, then C is M divided by L. So I'm going to plug that M divided by L in for C. One of the 3 L's cancels this L in the denominator, and I get the familiar 1/12 ml squared. So this is how you integrate to show that the rotational inertia of a bar about its center is 1/12 ml squared. And hopefully you've seen that before. You might not have memorized it, but you're like, hey, I remember that the rotational inertia about the center of a bar is 1/12 ml squared. I might have been taught that at some point. You didn't memorize it, but it sounds familiar, right? Okay, so now I want to talk about something called the parallel axis theorem. So you remember a second ago when I held my barbell and then I tried to hold it by the end and the rotational inertia was bigger? Well, there's a mathematical theorem that lets you take the rotational inertia about the center mass and change it into the rotational inertia about a parallel axis that is not through the center mass. So the white dot is the center mass. Suppose instead that I wanted the rotational inertia if the red dot was where the axis went through, right? Instead of the white dot, right? So I wasn't able to label it on this diagram, but the center mass, the white dot, and the red dot where we're going to rotate around, those are going to be a distance d apart. So the red dot is d away from the center mass. So how do we find the rotational inertia about the red dot, which we call I subscript d? What we do is we use the I about the center mass, which we call I subscript center mass, right? And this formula, the I about the red dot is just the same as the I about the center mass, but you're going to add to it the full mass of the object times d squared. D is how far from the center of mass you are. So it turns out that the center of mass is where you put your axis to get the lowest rotational inertia. The lowest rotational inertia possible is at the center of mass. That can be proven and has been proven, so I'm not going to prove it for you because somebody else did. But if you put the axis anywhere other than the center mass, the rotational inertia is bigger the farther the axis is from the center mass. So if you pivot about something that's not the center mass, you get the full rotational inertia as if you were about the center mass plus extra based on how far from the center mass you have pivoted. So you're going to take this idea and you're going to riddle me this. Okay, and this is called the parallel axis theorem. What is the rotational inertia about one end of a rod about the center 1/12 ml squared, but about one end, well, I want you to use the parallel axis theorem to figure that out. So 1/12 ml squared in the middle, how are you going to get out to the end? What is the D value going to be? And what happens when you get all the fractions together? Okay, 2 minutes. On your mark, set, go. you're listening to all this through headphones, I apologize because now your head feels lopsided. Okay, so let's apply the parallel axis theorem. So the I about the red dot is the I about the center mass plus md squared. The I about the center mass was 1/12 ml squared, we found out from that integral, and the d distance from the center mass to the new axis is 1/2 L. So we're going to plug that in, 1/12 ml squared, and m times half of L squared, that winds up being 1/4 ml squared. 1/12 ml squared, 1/4 ml squared, a 12th plus a 4th winds up being 1/3 ml squared. And again, I'm hoping that this sounds familiar to you. Hey, I remember learning that a rod about one end is 1/3 ml squared. Well, here we just proved the two rods rotational inertia formulas, first through integration, then through the parallel axis theorem. Okay, so here's the diagram of my slow-yo. And so what I had was okay, so I used the wire hangers, but here I'm kind of showing like these are pieces with little holes in them where these four spheres could be attached in these little rod pieces. If you use like physics stands or something in your classroom, you'll know what I'm talking about, those long metal pieces with the holes in them, right? Okay, so what have we got here? What we've got here is we've got these four little masses, and so the total of the little masses is m, and the masses are way heavier than the rest of this contraption. So that's going to be a key point here, that the four little spheres are pretty much hold all the mass. Their distance from the center is lowercase r. So lowercase r is the distance, the little spheres. And I made capital R the radius of the central axis, and the length of the string is d. So I'm going to propose to you that the time it takes for this whole thing to unroll is given by this equation down here. So we have this equation down here, and I want to say that that equation tells us the total time that it takes for this whole thing to unroll. Turns out this equation is completely wrong. Your job is not to tell me what the right equation is. Your job is just to tell me every aspect of this equation that is not plausible. In other words, every aspect of this equation that can't possibly be right. If that increases, the equation says this increases, but really this should decrease. That kind of reasoning. Okay, so I'm going to give you 3 minutes to find everything about this equation that communicates wrong relationships. On your mark, get set, go. Okay, so what is implausible about this equation? Turns out everything. Every one of those letters is in the wrong place. This equation states that better gravity would take a longer time to unroll. Look where G is in the numerator. That equation with G in the numerator says more gravity takes more time to fall. That's ridiculous. Gravity would pull harder, increasing your acceleration downward, and would take less time. G should not be in the numerator. It should be in the denominator. This equation says that the longer the distance to fall is, the less time it takes to fall. Are you kidding me? That doesn't make any sense. This does not make any sense. And if Chewbacca is from Kashyyyk, this does not make any sense. No, I'm kidding. Okay, that's a reference to a TV show. Anyway, so distance should be in the numerator, right? That what I'm seeing in this equation doesn't make any sense. D should be in the numerator, so it takes more time to fall for more distance. Turns out both the R's are in the wrong places. The big R should be in the denominator because the bigger the axis is, the more torque there will be, R times F, right? The bigger the torque, so the longer, the faster it'll accelerate, and the faster it'll go toward the ground. It'll take less time. So the big R should actually be in the denominator. More central axis radius, more torque, more angular acceleration, less time. Whereas the little r should have been in the numerator. The farther those masses are, the less time it will take for them to, the farther the masses are, the more rotational inertia there is, and the less angular acceleration there will be. So that'll take more time. Okay, so we're going to venture into a couple of these where we're going to do some experiments. So let's talk about formulating experiments that could be used to calculate rotational inertia. So I want you to pretend that the big giant wheel from The Price is Right is coming to your classroom, okay? So we're going to bring the big giant wheel from The Price is Right into your classroom, and let's say that the bearings have no friction. Obviously, the bearings have to have friction, or else Bob Barker or Drew Carey and the contestant would just stand there forever, and the wheel would just keep rotating and never stop, right? But let's pretend like with no friction, this is the wheel from The Price is Right, and you're going to use anything that you've seen in your classroom, but you're going to do an experiment to measure the rotational inertia of the wheel. Now, the timer says 5 minutes. I think I'm only going to give you 3 because otherwise we're going to go over time. So let's take 3 out of these 5 minutes, and I'm not going to just leave this animation here for 3 minutes. So 3 minutes, I want you to sketch out the fastest procedure you can. How would you find the rotational inertia of this gigantic wheel if it were in your classroom and had no friction? On your mark, get set, go. We're only going to go until it says 2. So we're going to run out of time. said I wasn't going to spend this whole time here. Okay, so here we go. So there's a lot of different ways you could do it, but just make sure that whatever you said, first of all, there's some way to measure some kind of torque. So you're going to apply a torque and you're going to figure out a way to calculate it, right? So I'm thinking you could wrap a string several times around the wheel. You could pull with a spring scale with a constant force. You read the force off the spring scale. You hold a meter stick up to the wheel to get the radius. Force times radius gives you torque. On the actual show, people actually who are short will actually jump up and grab on and use their own weight to pull down on the wheel. Heck, I'll take that too. So what you could do is just jump up, grab on, and pull down with your own weight, but then you got to measure your weight because that's the force. So maybe a scale. Meter stick gets the radius. I didn't spell out the rest of that, but it's the same idea. Torque is force times radius, right? Okay, so now you've got your torque. So now how are you going to figure out, let's say, the angular acceleration? So you needed to mention angular acceleration, right? So you could have said, hey, I'm going to time one full rotation while I'm pulling the rope. Okay, so one full rotation is 2 pi for a theta, time how long with the stopwatch, and then do theta equals 1/2 alpha t squared to get alpha. Another thing you could do is you could pull for a certain number of rotations, that gets you the theta, and then you can time one period after you stop torquing it, and that would get you the omega. Omega is 2 pi over 1 period after you're done torquing it, and then use like omega squared equals 2 alpha theta. There's another way with omega equals alpha t that you could have used, but you had to talk about making a torque happen and measuring it. How would you make measurements of time, theta, or both to get alpha, and then torque equals I alpha, and that would get you your rotational inertia. So that's the 3 prongs of your procedure. Okay, I had one more. We're not going to do it here. I'm not going to time you for 5 more minutes. I'm already way over time. So here's the deal. If you're watching this live, I'm about to go over the rubric for this. I'm not going to give you the time to do it. Deal with it, all right? If you're watching this, whatever the opposite of live is, dead. If you're watching this dead, then first, please don't eat my brains. And second of all, you can pause the video after I set this up, try it on your own, then see the rubric. But I just want you to imagine you have a baseball bat, and the baseball bat can be attached or unattached to an axis that it can swing from, like these rods. I did not animate a baseball bat. Just imagine these rods could be like the baseball bat. So how could you take this baseball bat and either off or on or both of the axis that it could swing down from? How would you measure its rotational inertia? Okay, so about that point where it's fixed to the axis, right? So here's the rubric. I'm not giving you the 5 minutes, so here we go. So it's a 10-point rubric. First, you had to talk about how you're going to get the mass of the bat, put the bat on a scale. Then you needed to talk about the fact you need to find the center mass of the bat. It turns out that's important. So you say, I'm going to find the center mass of the bat, and then you give me a way to find the center mass. Like you say, I'm going to put it on a table, and I'm just going to gently nudge it over the table. And once it tips over the table, that's where the center mass is where it's at the edge of the table, right? Then you fix the bat to the axis, and you're going to displace it to the side some. Okay, now you're going to measure with a meter stick how much the center of mass changes height. Why would you measure how much the center of mass changes height? Because you're going to use mgy to get potential energy, and potential energy is always measured to the center of mass. So wherever the center mass is, however many meters it goes up, that's your y. Mgy gets you potential energy. Now you're going to take the bat, you're going to let it go, and it's going to swing through the vertical. So now you got to talk about how you're going to find the speed of it as it goes through the vertical, right? So you could use a photo gate, or you could use maybe a video, right, where you go frame by frame in the video or something like that. But how did you find the speed through the center? Then you use V equals omega R to get the omega. So the R would be the distance from the pivot to wherever you were watching to get the V, right? Okay. Then if you have omega, then you can write this equation. Mgy, you know all those numbers, that's potential energy, equals 1/2 I omega squared. You got the omega, you can solve for the I. Okay, I'm way over time. Here's the summary. Rotational inertia is how difficult it is to change an object's motion. Depends on the mass and how far it is from the axis. If you change the axis, you change rotational inertia. You can use integration on basic geometric shapes to find rotational inertia for a direct calculation. But for real life objects, you pretty much have to use an experiment to find rotational inertia. Okay, I forgot to do this last time. I forgot to to include some practice problems. I've gotten some feedback that y'all really like that. And the last two that I did, which was center mass and power, rarely showed up on free response, but momentum and collisions, which I did yesterday, really does. So you'll see here, and it's actually the last one is cut off. So let me read it off to you. It's 2019 set 1. There were 2 sets in 2019. It's question 2, and all of these are physics C problems. None of them are B or 1 or anything like that. And then there are 2 that are really good for talking about rotational inertia. So 2 good ones for rotational inertia, and then these 10 or however many there are there for momentum and collisions. The last one is 2019 set 1, question 2. So if you need to pause and go back and screenshot this, it's all good. But as for me, I'm going to go ahead and call it a day. I will see y'all next week, and then I will see y'all for the practice exams the week after that. Have a good one.
Phew.